All right, hello everyone. It's December 13th. All right, let's do this. Oh, wow. It was just solved not a long time ago. Continuous subarrays. You're given zero indexed integer array. A subarray of nums is called continuous if I to j be the indices of the subarray, and for each pair of indices, each pair of indices. No, the difference is smaller than the absolute difference is smaller equal to 2. Return the total number of continuous subarray. Each pair of indices. 5, 4, 2, 4. 5, 4, 4, 2, 2, 4. 5, 4, 2 is not, right? Because 5, 4, 2, 5 and 2 is bigger than 2. So 4, 2, 4 is. Yeah, 1, 2, 3 is everybody. But you cannot do the and add 2 to the minus 1. It's the total, right? But we're looking for subarray, and I say every pair of indices. Okay, every pair of indices in the subarray. We want a total number of continuous subarray. Every pair. So if we find a subarray that's good, then everyone inside the subarray is good, right? So can we say have a subarray? Because all I need to keep track of a subarray is the min and max, right? If the min and max is the difference is smaller or equal to 2, and everybody else inside is difference smaller or equal to 2. So let's say we have 2 pointers, right? And one pointing at the beginning and the other just moving forward. And as we go through, we will keep track of the minimum, right? We keep track of the minimum, and as we go, every time a new one, we can compare, right? We can compare, and then until we hit a number which is bad, then the previous subarray, every single one in it counts, and that's 2 to the power minus 2, because you cannot have an empty array, right? So you save that, and then you start to reduce from the left, right? You start to reduce from the left, because you know the current range is good, right? The current range is good, everybody's good, and you start to pop on the left. Until you hit Yeah, because you add the current one, right? You add the current one, so you need to pop until the smallest one gets popped. Right, now you have the new one. So we do have to use a priority queue still. Right, we still need a priority queue. 2 pointers and a priority queue. Yeah, so just keep pop until we pop the smallest. Right, we pop the smallest, and then wait, hold a second. No. We'll keep moving the index forward. Right, index forward, index forward. We move the index forward, and we'll pop it if it's the smallest because I move I forward, right? I forward. So we check the top. If it's larger than, then I need to keep going. But if it's smaller or equal to, then I pop it, right? And if it's smaller or equal to, I pop it. So kind of you need two. So yeah, one is to move I forward, right? So basically you say, because you want to pop that. You can pop the smallest, and then you move the index to this 1 plus 1, right? And then you just popping everything until you hit something that's no, we need an I because we need to know the length. Okay, so if we hit something that's too big, then we don't add it, right? We don't add it, we handle the previous, and then we start to pop. Right, now we start to pop. We'll pop until it's good, but how do we do? How do we do the index? Because index wise, I will just keep moving forward. Right, I'll keep moving forward. I need to move forward until a point where everybody in it is wait, how do I do this? We have the index, right? Because it's bad, so index just move forward, right? And I check if it's equal to the smallest. If it is, then we'll pop the smallest, move it forward. Yes, yes, yes. We just keep moving the index forward. Right? Keep moving the index forward, and and if the smallest is still too small, then we keep moving forward until we pop all of them. Yes, we pop all of them. That's okay. I have an idea. Let's try it. Oh, I feel my brain a little bit slow today. I think this is what I need to get a main heap. And then we need a, let's say I equals 0. Okay, and then we'll have a long rest. Right, so each one, before we add it, we'll check hold on, I think we can, let's turn this off. Alright, so before we add it, so we'll check, right? Usually we say, and then we will add it. Right, so basically say while. Say while pq.empty. Right. Huh. Something is not right. Okay. Something is not right. Oh, I think I got it wrong. Hold on. Priority queue. Oh, you put it inside. Oh, my bad. Yeah, that is completely wrong. There we go. Now I can say pq.empty. Right. So while pq is not empty, and we say nums I is not equal to pq.top, right? Then in that case, I need a plus plus, I need a plus plus. We'll move I forward. Is that right? Hold on. What we want is PQ is not empty, and current minus that So we keep the minimum. So just current minus that. Or what if current is smaller? Yep, doesn't matter. Smaller, bigger, it's... Yeah, what if current is smaller? I need a sorted array. I need the biggest and the smallest. Because if current is much smaller, then we need a max heap, right? To keep track. So I do need something that can keep sorted the whole time. Yeah, I need something to keep sorted the whole time. So I need to keep track of the smallest. I need to keep track of the biggest. Because if only the smallest, alright, if only the smallest, what if the current one is smaller? Right? The current one is smaller, so I need a bigger one to also indicate that, yeah, it's not possible. Ending at this is not possible. Alright, so I need the small and the big, so that the current one, it has to be in between, or not like deviating too much. So if that's the case, you just add it to it and then keep moving, right? You keep going until you hit something that's outside this range, right? Yeah, it's outside this range. Then you do a computation, and then you start shrinking, right? So this is the difficult part, because when you shrink, how much do you shrink? So each time you shrink, and how do you remove a number from it? Okay, we can keep two, right? We can keep two priority queue, right? One is the min heap, the other is a max heap, right? Okay, so now I have a max, now I have a min, and if it's outside the range, then we will just start shrinking. Actually, I don't know. Do we need to? We don't need to move I forward, because if it's outside the range, like if you're small, or if you're big, you're too big, right? So we get something that's too big. If it's too big, then we'll stop popping. We'll stop popping the min heap, right? And we pop the min heap until the smallest is good. Then we know, right? Then we know the index of the smallest, right? So basically just saying from that index forward, nothing is smaller and everything is good. Okay, so I have the index, and the max heap do the same thing. So also the difference. So we just pop, right? So at the end, what we have is the min heap and the max heap, the top. The index is where we are good. That means we do need two of this, right? And we're gonna do a pair of int and int, right? And this is gonna be pair okay. So I'm not sure if I can do this. can say this is the min heap, right? And then we can copy exactly this, but without this part. This is gonna be max heap. I may spell it wrong. So I don't need this, right? So we say while main heap is not empty, and actually I can use I, and nums I minus the mean value. So we say min heap dot top dot first, right? If that is larger than 2, then min heap dot pop, right? Then we check the next one, we check the next one, we check the next one, and then we do the exact same thing. But this time with a max heap, right? And for max heap, we'll do the max heap minus, right, minus nums I, then max heap pop, right? Max heap pop. So eventually, what we have is in the max heap, the top is the index of the max heap. And then the other one will be the index of the min heap. But that's just the smallest, right? But I could have other things in the front. Oh my goodness. Yeah, so add, and a new one, right? And then I have a min heap. Yeah, think about it. You have a heap, right? And then you start going one by one, and each time you add a number to it. You add a value, you add, and then the smallest will go to the front, the biggest will go to the front, right? That's fine. And eventually you hit a number that's bad, right? That's bad. So you handle the previous one, right? You handle the previous one, and after you handle the previous one, now you need to consider your current value. You want to add the current value in it, but the current value you cannot add to it until you deal with the current situation, which is you pop the front, right? Pop the front, and then you pop the front. So each time you pop, you have a front. So we do need a, so I have to go with J at the front. That's fine, right? So first things first, right? If nums I minus min heap dot top dot first is larger than 2, or max heap dot top dot first minus nums I is larger than 2. So if any one of this happens, that means the current number has to be handled. Not handled, we have to deal with the previous, right? We have to deal with the previous. Now, how do we deal with the previous? We say rest or plus equal to long 1 left shift I minus j plus 1 right, this whole thing minus 2. Right, so this is the previous round was good, so I handle, actually hold a second, it's actually not I, because I is not part of it. It's I minus 1 minus j plus 1, so I can remove that. Okay, so if this is bad, I do this, and in fact it's a little bit more complicated than that. So we need to pop it, right? So when we pop, we need to update, right? Update the current j value, right? Because j is at the front. And update the current j value. Now, how do we update the current j value? Every time we pop, then we know that this, like all the things before this, is bad. So I can say j shall equal to std, right? Max of min heap dot top dot second and j, right? I update j. Actually, no. This shall be plus 1 because this 1 gets popped. So it has to plus 1. And we go through that, right? This is all the j. And here, essentially we do the same thing, okay? We do the same because the max might be at the front. So we do the same thing. We say max heap dot top dot second plus 1 j, right? So we do this after we run through this, then we get the j value, which is the front of allowable, right? Allowable start. And once we've done that, we say the main heap dot push nums. Ooh, that is actually an interesting idea. You don't have to use a pair. You just need to push. You just need to push, right? And all we need is that is actually correct. All we need is the indices, because the size we can, okay, how do I do that? I have this, I need a, because I need to use a lambda. Okay, hold on. Oh, I'm gonna change this. Jeez. So we say auto compare mean compare, right? Mean comp, and we'll say int a, int b. I think left and right is actually good, right? And then what? This return so I think it's return true if this is at the front, right? Return true, then this will go to front. Actually, hold on, let me read it again. It return true if the first argument comes before its second argument in a weak ordering. But because priority queue outputs largest elements first, the elements that come before are actually output last. That is, the front of the queue contains the last. Okay, front of the queue contains the last. So if it's mean, then we need to reverse it, which means nums left larger than nums right, right? So this is the situation where And this one, the second one, goes to the front. And we'll do exactly the same for this, but this time we'll call it max. So max will be the opposite. Okay, and we are going to completely redo this. We're going to do this. So it's going to be int, right? Vector of int, and declare type of min comp, right, of this, and then we need to pass min comp. Okay, this is the same here. Int std vector int declare type max comparison max heap. Ooh, I forgot this. Okay, so now we have this, Alright, let's just change it. I like to say this is I, this is J. Sorry, I just can't wrap my head around if we do it the other way. Alright, so now we say dot top, right? This is the index. So I can say nums, right? This, then we'll max heap dot top, what's the same thing? Nums this value minus is larger than 2, right? So if that's the case, then rest of plus equal to I minus j. Yeah, I think this one is still holds, right? It still holds. It's just saying we add a current one, it cannot make a good. And this needs to change. So this will be nums top, right? And this is going to be I equal to this. Yep, I can just do the top I. And here is the same. This is going to be nums this, right? Ugh. Minus I, and then this is I. Heap this one, not necessary. And this is gonna be I. Oopsie doozy. This should be J minus I. So J minus 1 minus I plus 1. And then when I push, I just push I. Push also. Oh no, this is J. Okay. Nums cannot be implicitly captured in a. Ooh, I think do this. Okay, so we might need to do like we keep going towards the end. Let's say. Oh shoot, it is nums j. Damn. Oh shoot. Alright, it's nums j. And this is I, update is I. So nums has to be j. Okay. So at the end, the last one, if it's bad, then we will do this. And we'll do that, right? Now if it's good, then we add it, right? So now we get out, right? Now we get out. We actually have a new one, which is n, and I just need to know the I, right? So n minus I. Yep, so I need to return, okay, rest plus long 1 left shift n minus I minus 2. What? Oh, oh shoot, my bad. I put it in the wrong position. Okay, now I think we're ready. I was quite slow today, mainly because I was the head was not in the right place. Where? Constant no pointer of reference binding to no. I have no idea. It could be this. Not sure. I think we need to write test case again. Wow, every single it become a thing. It seriously become a thing. And I'm not appreciating this because this one is not that hard. It's just you know, things like this happen and then you just have to deal with this. Okay, let's see if this one wrong, this one's not wrong. Can I do this? Can I do this? Okay, okay, okay. Oh, this is wrong. Yep, because oh my god, I have to say main heap. Oh my god. Okay, so basically it's gonna be main heap is not can we make it easier? I just figure out, I think we can make it easier. Because every time you add one, then you just add that number. Which means every time you add one, right, then you get a new length and then you just add that length because there's 1, 2, 3, right? So I don't have to do this, nor do I have to do this. So I always add them first. Okay, so we add them first, then we decrement it, and once we decrement it, rest plus equal to long j minus I plus 1. right? And I think with that, I can just return res at the end, because the last one when I pushed in, I'll be popping and I'll handle it. Okay. Okay, so you wanna just take a look. Answer is 8. Is that 8? Answer is 8. All right. This is actually better than the previous one. I think it's cleaner, and then it gets the job done. All right, it gets the job done. Two, 6, 2. It's not hard, but I think it's not hard. Just two priority queues, one max heap and the other min heap. For each new number encountered, we put its index, right, in both heaps, and then pop the heaps if the top, if the min or max values, min or max values exceed the requirement with regards to the current number, right? And each pop help us find the start of the current continuous subarray that ends at the current number. Right? So you get smaller, use pop, 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 and it was good. Right? That's the smallest. And then I'm just thinking if I need to also pop the ones that don't belong in here. Because I have I, which is I got a maximum, right? What if so the smallest has index of this, right? And if I have something that's also small, because it happened later, and that one will get popped, right? And yeah, and everybody else is bigger. Everybody else is bigger, even if it's bigger at the front. Like, it doesn't matter, right? It doesn't matter, because yeah, it simply just doesn't matter. The big value can be in there, it doesn't matter. Okay, so let's submit it. Hopefully one shot will get it. I'm really tired. Alright, hopefully one shot will get it. Yes, one shot we get it. It's pretty good, pretty decent. I didn't write the complexity, but that's okay. Oh, sorted map. Oh yeah, it has sorted map, right? Priority queue. Yeah, you have the two, a min and a max. Push, push, pop, pop, do this, right, plus, plus. Yep. Oh, you can do monotonic. Optimize two pointer. What's this? Do a map? current element to the frequency map. So frequency dot begin first minus frequency dot r begin as the end. Also, you add it to it. So if it's larger than 2, then you remove the leftmost element from frequency map. So it will remove, and if this is equal to 0, then you erase. And the left plus plus. Huh? Oh, this is moving the, okay, moving the index. Oh, this is the ideal of a sorted, right? Yeah, so you just, like, because right now it's bad, right? So you move it forward. So you remove this number and you just check remove forward and move forward until you get to a point where it satisfies. And then that's your current. Okay, yeah, that's fine. O(n) log k, and this is O(n) log n. Ah, because it's sorted on k. Okay. How do we do that? So we have a deck. Max Q and min Q. Oh! Damn, I forgot. Yes, that's correct. Max and min. A min, a monotonic increasing, a monotonic decreasing, right? So if it's increasing, I have the biggest. Wait, hold on. Increasing, I have the smallest. Increasing, I have the smallest. Okay? At the front, right? Increasing. And then I can, every time I add it to it, so all the big ones gets popped. Yeah, what if I'm adding myself? I am the smallest. The smallest. Then I need to know what is my left, right? I actually don't know. If max Q number is smaller than the right, then we pop back. So it's increasing, a max is increasing. Min, if it's larger than you pop. Okay, have a min Q. Decreasing monotonic deck for maximum values. Increasing monotonic, that's just decreasing, this is increasing. Anyway, so use this to keep the max, use this to keep the min. And then you have max and min, which is at the front, right? Which is at the front. Oh, it is decreasing. Yes, it's decreasing. So you have max and a min. So if max minus min is good, then you use those. If you're not good, as you currently, you just add the new value in, right? So if they're not good, it's because the new one added, right? So if it's larger, then we move left pointer. So we have a left pointer. So we move it forward. Oh, depending on who is at the front. Because I have a left max Q front. Yes, because if it's a very big value, right, then if it's bad, so the current one is this, and then, so it's bad. So it is from this, right, all the small values, right, all the small values in this range, and basically I go through them all, and we'll stop at 1, which is good. Pop front, okay. Right, you just get a front, you get the end, you +1, you get a left, and just keep going until it's good, then you add it. Okay. Current min and current max. Expand the left boundary. Nope. Yeah, I think the best one is this deck solution. I mean, it's essentially the same as priority queue, but you're using a deck to do priority queue, right? I still couldn't wrap my head around, because I feel always if you have priority queue, no, if you have deck, a monotonic deck, you are losing some information, and what you're saying is lose those information is fine, because I'm just imagine if I have a monotonic increasing array, right? A monotonic increasing array will keep track of the minimum value. And if I come in as the minimum value, and I'll pop everybody, right? I'll pop everybody. And once I pop everybody, then I am the smallest, right? Then I need to go check. Now that's actually true, because you just want to know the biggest one so far, right? The biggest one so far, and then you need that one to move. Yeah, you pop it. You pop it on the left, and then will be the second biggest one. Uh-huh. And you use the method just simply to check. You use this to check who is at the front. Yes, who is at the front? Because whoever is at the front need to move forward. Yes, that is true, which is essentially the same as this one, right? You just, but this is popping based on the size, but this popping is based on the position. Whoever's at the front gets popped. Whoever's at the front gets popped until we return to the, and everything that's removed in between is fine. Yes, everything removed in between is fine because they are indices are also in between the two, right? Therefore, if you pop this, you pop the smallest, and you need to use the second smallest. If there's any value between the smallest and the second smallest, any indices point to the values that's bigger, that's fine, right? Because we're not going to use them anyway. Yep. This is the best solution. And I think it deserves some attention. We're going to write this one more time. Not today, right? Not today. We'll do it another time, but we'll have to do. Yeah, it's only 1 year ago. Oh my god, that's exactly 1 year ago. Exactly 1 year ago. Wow. Very interesting. Oh, are you kidding me? Wait a second. Really? Not only is it exactly 1 year. Okay, not only is this exactly 1 year ago, I submitted exactly the same time. And I'm gonna do something similar as well. As to use the monotonic array method. Wow, this is a wild. This is a wild. All right. Anyway, I'll see you guys tomorrow. Adios.